Good afternoon, everyone. Can you hear me all right?
Yeah.
Yeah.
Very good. Do we have any questions before we start today's material? Anything on 3.1 or 3.2?
I have one.
Sure, go right ahead.
Okay, so it's 3.1 and it's question 53 from the homework.
3.1, 53. Let's see what that looks like. 3.1, 53. Okay, let me see if I can write that out so we can see it.
It's the interest problem, Professor.
Okay. 53, find the accumulated value. So we're asked to use compound interest formula. Let me get this out of the way. A equals, the amount equals the principal amount times 1 plus R over N times T, where T is the number of years and N is the number of compounding periods. Let's see, 53 to 56 gives us A equals PE, continuous compounding rate times time. Okay, so find the accumulated value of an investment of 10,000. So if we use, let's see, what formula does it want us to use here? Okay, we're going to use several of them. Compounded semi, compounded quarterly, compounded monthly. So if we're going to do that, we're going to use this value here, aren't we? So if it's compounded semi-annually, it's compounded twice a year. So at semi-annually, we compound it twice a year. So if that's the case, N is 2. So A, the amount we receive is, and we're given P equals 10,000. So that's 10,000 times 1 plus, and the rate we're given is 5.5%. And when we're using interest calculations, we use the decimal form, don't we? So that's 0.055. And we're doing it semi-annually, so N is 2. And number of compounding periods, N is 2. And we're going to do it for, what does it say here? 5 years. So T equals 5. So that's going to be 5. So let's see if we've got our, we know he's doing this calculation if the numbers are wrong. So the amount we're going to receive is going to be 10,000 plus this rate of interest here, 0.055 over 2. That's compounded semi-annually. So we're going to have 2 compounding periods a year for 5 years. So that should be the equation we want to use, which should be the main issue. Once you've got the equation, you just have to plug that into your calculator to come up with a number. So does that answer your question on which equation we would use?
I'm still a little bit confused on like how you knew to use that equation other than the other one.
Well, this is continuous compounding.
Okay, so that's just the continuous.
This is continuous, and this is for N periods for T years.
Okay, so for A through C, you'd use the longer one, and then the shorter one would be the B.
Yeah, continuously would be this one.
Okay, cool.
And for a specific number of years and a number of periods per year, we would use this guy here.
Awesome.
Okay, so then once we've got this and we plug that in, and I think we get a little over 13,000 on that. I think it's 13. Let me look that up. 140. No, one
It's 1,316 and a half. Yeah.
and 51. Yeah. Okay, questions on that at all? What we did there? I guess the main thing is we want to make sure we find out what's given to us. The original principal amount, the interest rate, and the number of years. And then we plug that into, this is a continuous formula. This is a formula using these values here. Interest rate and compounded semi-annually or quarterly would be 4. N equals 4 for quarterly and so forth. Does that answer your question okay? Which formula we use and how we plug that in? Okay, other questions before we get to today's work? The plan today is to cover 3, 3, 3, 4, and 3, 5. So I'll put the book away then and get out 3, 3, 3, 4, and 3, 5. 3, 3 talks about properties of logarithms. So we're going to have to kind of define the logarithm again. We'll make sure we understand what that is. And then the objectives are shown as using various rules for logarithms: product rule, quotient, power. So those are the rules. We're going to make sure we understand them, what they are, and how we use them. And then we'll expand some logarithmic expressions and condense some. And then we'll use the change of base property. Okay, so that's the plan and what we're gonna do. So let's take a look. Maybe I can grab this piece of paper back here and talk about some rules. Well, let me get a new piece of paper for the rules in case we have to go back to them. So I've got a product rule. And the product rule, remember when we had properties of exponents? And we said if we have a base to some exponent and times that base to some other exponent, base to the m times base to the n, we have a common base. And we say that's b to the m plus n. Okay, so that's how we combined exponents when we had a common base. Now we remember when we did our definition that a log is an exponent. So if that's the case, then if I take properties of logarithms, then I can say if I have log, I'll just do a lowercase to try and be consistent here, log to some base of quantity m times n, that's going to be equal to the log to this base b of m plus log same base of this value here. So this says then that the product, the log of a product, equals the sum of the logs. Okay, the log of a product is equal to sum of the logs. Here's the log of a product. Here's the product, m times n is equal to the sum of the logs, and we're at the same base. So log base b of m, log base b of n. Okay, and that's called the product rule. And we're going to use that in some specific examples. And I'm going to just list the rules first, and then we'll take you through some examples. We also have a quotient rule. And we came to exponents. We said that b to the m divided by b to the n, that gives us a quotient, doesn't it? And again, common base. So with a common base, then we said that's equal to the base to the power m minus n. Okay, remember that? And so we call that the quotient rule. And when we apply it to logs, we have, for instance, log base b of m over log base b of n. And that's going to be above, we had a product. We turned that into a sum. When we have a quotient, log base b of m minus log base b of n. So here we have a difference of logs. Here we above we had a sum. Here we have a difference. Okay. Questions on that at all? Sum and difference?
Wait, could you explain the quotient rule again?
Yeah, on the quotient rule, we're going to do remember like we did on exponents, and we said, well, we have a common base, so we're going to subtract. So we're going to take the denominator from the numerator and say m minus n. For logarithms, keeping in mind that a log is an exponent, then we can kind of see logically how that follows. If we have a quotient log b of m, we're going to subtract, just like we did here. We have an exponent m minus n. Here we have the log base b of m minus the log base b of n. So it's a difference of logs. Okay. Now we also have a power. Go ahead.
Sorry. So yeah, to be clear, so like we said that the log of a product equals the sum of logs, we could say the log of a quotient equals the difference of the logs.
Anybody, can any other students answer that? That's what we wrote here, isn't it?
Okay.
Log of a quotient is the difference of logs. Okay, is that clear?
Yeah, thank you.
Okay. We also have a power rule. And the power rule for exponents, we said, well, if we have some base to some power n, and we multiply that by another power n, then we say that's base to the m times n. When we do that with logs, if I have a log to some base of m, and that's raised to some p power, I'll use p for power, then that looks like this exponent becomes a multiplier, and that becomes p times the log of m. So that's the power rule. In exponents looks like this, and in logs it looks like this, where this exponent becomes a multiplier. Okay, questions on that? And then lastly, I'm going to put up change of base. Change of base property. Change of base property, for whatever reason, we might want to change the base of some logarithm. We might want to say log base b of m, and we might want to change this base to some other base. And we can do that by taking that other base. Maybe instead of base b, we want base a. So we take log base a of each of these, this value here and this base here. So that becomes log base a of m. And we're going to divide that by log base a of the previous base, which was b in this case. So this will allow us to change the base by simply taking the log of the new base by this value that we're taking the log of, and then this value of the base. Okay. All right. Questions before we go into some more in-depth examples on this?
I did not get the last property, the change of base property.
What about it? What's your question?
I did not get how that works.
It's just a definition. It just says that if we want to change the base from b to a, then we take the new base of this value and the new base of this value, and we have a quotient. It's just a definition that we use.
Okay, thank you.
That's a property. Okay. Let me take you through some examples. If I have log base 6 of 7 times 11. And I say, well, let's see, that's a product. So by the product rule, I'm going to say that's log base 6 of 7. And because that's a product, I'm going to say the log of a product is the sum of the logs. So I'm going to say log base 6 of 11. Okay, so here we're using the product rule to expand this logarithmic expression. So here's a product, here's the sum of the logs. Similarly, I could say log of 100x. And I might say, well, let's see, that's a product, 100 times x, so that's going to be the log of 100. And then I'm going to add to that the log of x. And you notice when I do these, a book doesn't do it, but when I do it, I put the log as a function. In other words, log is a function. If you look on your calculator and you put in log, if I say log on my calculator, you notice it puts a parenthesis there, indicating that it's a function. So I like to remind myself and keep it in mind that a log is a function. And so when I'm doing it this way, I say, well, log 100 plus log of x. And then I know that log really means log base 10. That's short for log base 10, isn't it? So this says log base 10. So that says 10 to what exponent? A log is an exponent. So 10 to what exponent equals 100? Well, that'd be 2. 10 to the 2 is 100. So this value becomes 2 plus this value, which is log of x. Okay, so if I were to take this and say, use the product rule to expand this logarithmic expression, I would say this is a product, becomes a sum of logs, and then I simplify. Always be sure you simplify. So when I simplify, I take this value, say, well, that's log base 10. Well, 10 squared is 100. So this value becomes 2. And this value still becomes log of x. Okay. I might have a quotient rule. Let's see some examples of that. So I might say, given log base 8 of 23, for instance, divided by x. And I'd say, well, this is a quotient. Using the quotient rule, I'd say log base 8 of 23. And then I'm going to subtract log base 8 of x. And if I can't simplify it any further, then I say that's my solution when I use the quotient rule, using the quotient rule to expand this logarithmic expression. I might have a situation where I have, for instance, the ln, the natural log of e to the 5 divided by 11. And using my quotient rule, I'll say, well, that's the natural log of e to the 5, and then minus the natural log of 11. And then I want to simplify. So I take a look at my first term here and I say, well, the ln, the natural log of e to the 5th, well, this is base e, isn't it? So e to the what equals e to the 5th. Well, that becomes 5, doesn't it? So this becomes 5 minus the natural log of 11. So again, always simplify when you're going through these problems. If I take a look at the power rule, as an example, I might have log base 6 of say 3 to the 9th. And I say, well, if I have an exponent in here that the log function is working on, then that becomes a multiplier. So that looks like 9 log base 6 of 3. Okay. Questions on that at all? Okay. I might have log base b of say x to the 4 times the third root of y. And in general, when I'm working with these, I like to keep them looking like exponents rather than radicals. So if I'm looking like an exponent, I'm going to change this to log base b of x to the 4. That's an exponent. And this cube root of y looks like y to the 1/3, doesn't it? This is a 1 as a exponent, and this is the root here. So that looks like this. Now we've got everything in terms of exponents because I want those to come out and be multipliers when I separate this. So now I have a product here. And this becomes log base b of x to the 4 plus log base b of y to the 1/3. And so again, I want to continue to simplify. So this exponent becomes a multiplier for log base b x and plus 1/3 log base b y. Okay, so when I take and expand this using the properties, I end up by taking this product, expanding it into a sum of logs here, and then using my power property. So here we have a product property to get this this notation, and then taking the power property to get this notation. So now we've simplified all the way down to 4 log base b x plus 1/3 log base b y. Okay, and that would be the answer that we have. And we're not going to take these into decimals because we don't have any values here. We're not operating on any particular values. We'll do that in some later problems. Okay. Let's say I go the other direction and I want to write as a single logarithm. So I might want to condense. And if I give you log of 25 plus log of 4, let's say.
Professor, could you move paper up a little? Thank
Yeah,
you.
can you see that okay?
Yes, thank you.
All right, so this says well, we've got log base 25 of 4, a log base 10, isn't it? When I say log and don't give it a base, the default is 10, isn't it? That's what log means. If I look at my calculator here for the log function, that's the base 10, and this is base e, and those are important logs because they actually have buttons on our calculator. So if I'm going to condense this from a sum of logs to a product, I'm going to say that looks like log of 25 times 4, which looks like log of 100. And again, we want to simplify. So we know that this log is base 10. So 10 to the what is 100. Well, that's 10 to the 2, isn't it? So we can say then that when we condense log base 10 of 25, and I didn't even say 10, I just said log of 25 plus log of 4 is the log of 25 times 4, which is the log of 100, which is 2, because log is base 10. Okay, questions on that? Get a new piece of paper here. I think it's all fairly logical once you kind of get the idea of what logs are, what they're doing, and what the notation is for doing logs. If I have log of 7x plus 6, and from that I subtract log of x. Okay, so for this one, this is a difference of logs, so that's going to be a quotient, isn't it? So that's going to be an log of this log function is working on 7x plus 6 over x. So the simplified version then would be the log of the quantity 7x plus 6 over x. Okay. I might want to write as a single log. I might be given, let's say 2 natural log x plus 1/3 natural log x plus 5. And I'm asked to condense those. And say, well, let's see. This first one looks like the natural log of x squared when this multiplier becomes an exponent, plus the ln of x plus 5 to the 1/3. Okay. And because we have a sum of logs, then that looks like a product, doesn't it? So that looks like the product. We have a same base. So this looks like the product of x squared times x plus 5. So I've got this quantity times this quantity, and the ln is operating on that. And that's to the 1/3. Okay, this x plus 5 to the 1/3 is this value here. Okay. If we were doing if we
Right, I had a question on that.
go right ahead.
So I got how you made it to the exponent, but when you made 1/3 the exponent, I noticed that you made it outside the parentheses, whereas the 2 was inside.
Well,
So
it's outside. It's like going like this. It's like saying x squared, and this is x plus 5 to the, I could say squared or 1/3 or whatever. But the log function itself is working on this whole thing. So here's the first term, here's the second term, and the log function is working on the whole thing, which is this and this.
Just to clarify real quick, that 1/3 sits outside the parentheses, because if you put it inside, then it might get confused with just doing x plus 5 to the 1/3 power. Does that make sense, Gopal?
yeah,
This is
That's why
x,
it's sitting outside. It's the whole quantity of x plus 5 to the 1/3 power.
yeah, that's this.
so
It's
could we have-
inside the red paren, but outside this this pencil paren.
So could we have also done could we have put the 2 outside of the parentheses in
That's what I did right here.
okay.
Here's a paren, just to make it look the same.
Yeah, there's only one value in that parentheses, so it can go in or outside of it, because it's not going to get confused with only applying to one value. Does that make sense, Gopal?
You got it, Chris. Thank you.
Okay, cool.
Other questions? Okay. Let's see, what new concept can we do here? Let's say I want to evaluate log base 7 of 2506. And I can use that when I do log base 7, I can do that by saying, well, I can take, if I want to use common logs, I could say, do the change of base property then, which says that looks like the log of 2506 divided by the log of 7. Remember that change of base property we talked about earlier? So we could change log base 7 to, this would be log base 10. We could change it to log base n or e. The ln is log base e and so forth. Okay, so we can evaluate something that looks like this without having to find out a log base 7 as the actual function. We can do that, and I will show you that a little bit later, that we actually have a log base where we can put in a different base here. So if I said, for instance, log, this is an actual function that exists in your calculator. If I said 25 and 5, for instance, this is the base, and this is the value that we're trying to find. And we say, well, a log is an exponent. So 5 to what exponent? 5 to the 2 equals 25. And if I want to find that in my calculator, I could simply go to the math function here, which is this button here, and scroll up until I find the log base function, and then I can enter that. And if I put in 25 and 5, then I should get a 2, as we've shown here. Okay. Questions on that at all before I go on to something a little different? Okay. Let's see. Is there one I can have you do? Let's see. Now I think I'll stop at that point and go to the next section, make sure we've got enough time to go over all of our problems. So I'm going to stop at that point on section 3.3. And we've gone through the product and quotient and power rules and expanding and condensing and the change of base property. So with that in mind, I think I will go to the next section, which is 3.4, which is exponential and log equations. And we're going to use like bases to solve exponential equations and logarithms. And we're going to use the definition to solve some equations. Look at one-to-one properties and see if we can solve some actual problems using exponential and log equations. So with that in mind, let me see if I can find a problem or two that we can use. Get that out of the way, get that out of the way. All right, let's say I give you 5 and the exponent is 3x minus 6. And we want to set that equal to, let's say, 125. And I say solve. And you say, well, what am I solving for? And I say, well, you're always solving for whatever variable is not known here. Now, if we had 2 variables, then we would need 2 equations, but here we only have 1 variable. So I say solve for x. So when I'm solving for x, if I have the same base here and here, then I can set the exponents equal to each other. So I say, well, is there any way I can convert this to a base of 5? Well, 5 times 5 times 5, that's 25 times 5, that's 125. So that's 5 cubed, isn't it? So I can say 5 to the exponent 3x minus 6 equals 5 to the 3. Now, I could take the log base 5 of each side. And that would tell me that 3x minus 6 equals 3, doesn't it? So I don't really have to go through the idea of taking log base 5 of each side, but this tells me that as long as the bases are the same, I just have to set the exponents equal to each other. So I've got 3x minus 6. So I'll move that 6 to the other side. That'd be 3 plus 6, that's 9. And x equals 9 over 3, which is just 3. So then our solution, when we solve this, and we say solve for x, and I say 5 to the 3x minus 6 equals some value here, then I can, if I can set them up with equal bases, same base, then I can just set the exponents equal to each other. And that's what that's showing you. I might have 8 to the x plus 2. And maybe that's equal to 4 to the x minus 3. And I say, well, those bases aren't the same. And the idea is, can I set the bases the same? And I can say, well, 8 could look like 2 to the 3rd power, and 4 could look like 2 to the 2nd power, couldn't it? So I could say, well, let's see, 2 to the 3rd power times what? X plus 2 equals 2 to the 2nd power times x minus 3. So we've just replaced the 8 with 2 to the 3rd and replaced 4 with 2 to the 2nd. The exponents that were there originally remain the same. So now I can just multiply through. I can say 2 to the 3x plus 6 equals 2 to the 2x minus 6. And because the bases are the same, I can just set these equal to each other. So that can look like 3x plus 6 equals 2x minus 6. Okay, so bring the 2 to the other side, and we'll get 3x minus 2x equals, and bring the 6 to the other side, we get negative 6, negative 6. Combine these, we get x equals negative 12. So that when we have a to the x plus 2, set that equal to 4 to the x minus 3 and ask you to solve, that's the process that we could go through to solve. Okay, questions?
Wait, so on the problem like, on top, how'd you like use the log to get rid of the 5? Does that make sense?
This problem up here,
Yeah. How'd
First
you use
problem?
the log to get rid of the 5 to make it 3x minus 6 equals 3?
the bases were the same, weren't they? They both were base 5.
Oh, okay.
As long as the bases are the same, then we can set the exponents equal to each other.
Oh, okay. Sounds good. Thank you.
Make sense?
Yeah.
Other questions?
For the same question Alan brought up, is it log 5 on both sides you wrote?
I just said you could think of it that way. I didn't have to do it, but you could think of it that way. If I took the log base 5 of each side, I would just get 3x minus 6 equals 3, just like I got here.
Okay, thank you.
Other questions? Okay. Say I give you 5 to the x equals 134 and I ask you to solve. And you'd say, well, I have an exponent here. Now this is then an exponential equation, isn't it? And we might be asked to solve exponential equations, and exponential equations, our variable is in the exponent, as opposed to something that might look like x to the 5 equals 134. This would be a power function, wouldn't it? That's a power equation. We're taking x to this power. Here, x is the exponent. So here we would take what, the 5th root of each side, wouldn't we? And we get x equals the 5th root of 134. But here we're not doing that. X is the exponent. So whenever we're solving for an exponent, we can use the log, because log is an exponent. So if I take the log of each side, and I know that my logs that I have available as buttons on my calculator are nice. They're log and ln, which happens to be the log base e, doesn't it? Where log is log base 10. So if I take the log and I have a button on my calculator, I could say, well, no, I could take the ln of each side if I wanted to. I could say the ln of 5 to the x equals the ln of 134. And then I know by the power rule that this exponent becomes a multiplier. So that looks like x ln 5 equals ln 134. And if I divide through by my ln 5, I get x equals ln of 134 over the ln of 5. And depending on how the question is asked and what it's looking for, here's the exact answer. And we can say, hey, that's an equal sign. If I take, and I'm solving for 5 to the x equals 134, the answer becomes log of 134 over the log of 5. If the question says, give me the answer to 2 decimals, then I can enter this into my calculator. So why don't you do that? Go ahead and enter this into your calculator and tell me what you get for an answer.
Is it 3.043?
3.04. And if you're asked to round it to 2 decimals, it's just 3.04, isn't it?
Yeah.
Okay. Everybody okay with that? Everybody agree? Questions on what we did there? Okay. Say I have 10 to the x equals 8,000. What am I going to do there? We'll go ahead and solve that. Let's get a new volunteer to help us out with that one, so we don't have the same people having all the fun. Okay, do we have a new volunteer that can help us through this? Or should I call on a new volunteer?
Would you do like a natural log on both sides?
Ruthie, are you a new volunteer?
Oh, sorry.
We'll get to you in a minute if we need to, but I'd like to get as many participants as possible. Who else can help us? What new volunteer can help us?
So we would use the natural log, the ln.
All right, so if you want to take the ln, what is that going to look like then?
ln parentheses 10 to the x and
Okay.
close parentheses.
Okay,
Mm. On both sides.
both sides. Okay, ln of 8,000. Okay, all right. Is that it? Put a box around it and we're done. The question looked like this and it said solve, and it gives you 10 to the x equals 8,000. And we have an offering that says that's the same as the ln of 10 to the x equals the ln of 8,000. And the question is, are we done? Have any new volunteers that could help us out? Or Sam, you could help us too.
Bring out the x in ln to 10, so that's x
ln
times
10, okay, equals ln 8,000, okay. All right. Now what?
and then divide both sides by ln of 10.
ln 10, okay, so that goes away.
And
And
then we could either keep it that way for the exact answer, or we could put
okay,
it through a calculator.
so let's call that exact. And if we put it in our calculator, what do we get?
I got around 3.903.
Divided by ln of 10. Okay, and it looks like that looks approximately like 3.9. And if we round it to 2 decimals, it'd just be 3.90, wouldn't it?
So Professor,
here-
I had a question. So I got to the same answer here, but using a slightly different approach. So would that work on the test, or would I have to?
Well, if you got the same answer, what approach did you use?
I took the log. I took the log of both sides, and which I got then x equals log of 8,000, and which I eventually got to 3 plus the log of 8, which is rounded to 3.9.
Okay, so you said x equals the log of, you said 8,000,
Yeah.
and you put that in your calculator. Let's see if I put
No,
in.
I did x equals log. I used the product rule, so I did x equals log of 10 raised to the third power times 8, which equals log of 10 to the third power plus log of 8, which equals,
So you look like this,
yeah,
and then you said log base 10 of 10 to the 3 plus log of 8, like that.
yeah,
Okay. And the first gave you what? When you said 10 to the what equals this,
that
what did you
gave
get?
me 3,
You got 3.
yeah,
Okay, so you said log base 10 of 10 to the 3 is 3. Everybody else get that?
then I added that to the log of 8,
And you add that to the log base 10 of 8. And log base 10 of 8, you got 0.0903, like that.
no, I got the log base of 8 was 0.90.
0.90, okay. 0.903,
Yeah,
like that.
yeah,
Okay, 0.9030. And when you combine those, you got 3.903. And when you round it to 2, you got that.
Yeah.
Okay, so we're seeing that we can do the problem at least 2 different ways, can't we? One's using the LN, one using the LOG, and one breaking this up into a product. We wouldn't even have to break it up into a product, would we? If we just took the LOG of 8,000, if we take the LOG of 8,000, we get the value we want directly, don't we? 3.903. Okay, so you're seeing there are multiple ways to work these problems. There isn't just any one way, but always show me where your answer is by putting a box around it, putting an arrow to it, saying, here's my answer, because that's where I'm going to look, wherever you tell me your answer is. And I'll say, is that what the key shows for the answer? If the answer is yes, then I'll say, okay, that's good. Is there any work to show how you got your answer? And you might have work that looks like this. You might have work that looks like this. But be sure you show your work. Okay, so the 2 key points, show me where your answer is, put a box around it, put an arrow to it and say, that's my answer. Because as these problems get longer and longer, the work gets more and more, and you might be putting triangles and arrows and circles and who knows what you got on your paper here. And I can't be searching around to look for the answer. In fact, I won't be searching around looking for the answer. I'm just going to look at one spot, and that's where you tell me to look. And you say, here's my answer right here. And I'll just check it off and say, if that answer is correct, did you just guess at that, or did you have some work? No, here's some logic right here. Here's how you got the answer. Okay, does that make sense to everybody? Other questions? Okay. Okay, let's see, what else could we do here? How about, here's an interesting one. If I have a 7e to, let's say, the 2x minus 5 equals some value, 58. So this is given. And I say, I want you to find the solution exactly, and then I want to find exact and approximate. So let's say 2 decimals. Given that we have that. Okay. So if that's the case, the question is, are we able to solve this, and do we have a methodology that we can use to solve it? And we might say, well, how about we start separating this thing, take this 5 and move it to the other side. So we'd say, well, 7e to the 2x equals 58 plus 5. Looks like that's going to be 63. And I can divide each side by 7. 63 divided by 7, that's 9, isn't it? So that says e to the 2x equals 9. So now I'm searching for the solution of an exponent of an exponential equation. That's what this is, isn't it? Exponential equation. And in general, the way we want to solve these is with logs. And we say, well, we have a log base e. So I could easily take the ln, log base e of each side, e to the 2x equals the ln of 9. Whatever we do to the left side, we do to the right side. And this is log base e of e to the 2x. So this becomes a multiplier, 2 to the x, ln e equals ln 9. And then we take a look at this. What's the ln of e? Anybody, new volunteer for what's the ln of e?
Should be 1.
Are you a new volunteer?
I mean, I haven't answered a question in a while, but someone else can go. It doesn't matter.
Right, yeah, we want some new volunteers so everybody can get a chance to participate. So what do you think, Kyla, Laurel, Leo, Megan? What do you think?
It'd be 1.
And why do we say this is 1?
Because ln is an exponent and e will just have an exponent of 1.
ln is an exponent. Ln is a log base e, right?
Yeah, sorry.
So if I rewrote that, if I said ln equals log base e, and I said log base e of e equals some value, I don't know what it is. Well, we know that e to the x, because this is an exponent, e to the x equals e, this value here. So x equals 1, because e to the x equals e. Here's my base, here's my exponent, and here's the value that I'm taking the log of. So that's how we know that this value is going to be 1. So now we have 2 times x equals the ln of 9. Okay. So if we're solving for x, we can say then x equals the ln of 9 over 2. And that would give us an exact answer, wouldn't it? Okay. If you were asked to find that to 2 decimals, what do you guys get when you take that to 2 decimals? Kathy, what do you think? Kathy Tran?
I got 1.0986.
10986. And if I take that to 2 decimals, I'm going to get I want to round it to 2 decimals. What am I going to get?
1.1.
1.10. Okay. So this would be the approximate answer, 1.10, rounded to 2 decimals. That making sense to everybody? Questions on that at all?
I'm a little confused on when you did, so ln equals log base e.
Yes, up here.
Mhm.
Yes. That was
Okay.
that was confusing.
Well, I was just clarifying that point. And so, sorry. And so because ln equals log base e, and then you
Yeah.
did of e, and that equals x, and then sorry, but I can't. What's the other part right underneath?
All right, let me rewrite it. So I said log base e of e equals some value. We don't know what it is, so we'll put x because we don't know what it is. But we do know that a log is an exponent of this base. So this tells me that e to the x equals e. E to the x equals e. That's what this says, because a log is an exponent.
Okay.
So if a log is an exponent, e to the x equals e, and e by itself is really, we could call that e to the 1, couldn't we? So we could say, well, with the same base, x equals 1, or we could say e to the what power equals e? Well, e to the 1 equals e. So x equals 1 in that case, which is what we did up here. Does that answer your question? Is that okay, or do we need some more examples?
I think I understand. And so because and then with that answer, how
Mhm.
did you use that to find to solve the equation? Sorry.
Well, we have to decide what the question is. If the question is, let's see, I had up here, get a different piece of paper here. The question was 2 to the x times the ln of e equals the ln of 9. That was the original equation we were trying to solve, and we were solving for x.
Mhm.
So we said, well, I can divide through by 2. Those will cancel. And I can divide through by ln e. So now I've got x equals ln of 9 divided by ln of e. And I have to simplify. Now I'm just looking at one problem, which is what is ln of e? We want to evaluate that. So if you're looking at what's the ln of e, and we're looking at e to the x equals y, this is the exponential form. And if I take the ln of e to the x equals ln of y, then on the left side, I've got x ln e equals ln y. And again, we get back to what is the log base e of e. So you could think of this as an e as a subscript here if you wanted to, and say then this base to some power out here, I don't know what this power is, I'll just call it n, I don't know what the power is, equals this value here. So e to the n equals e. This to this exponent equals this value. Then n equals what?
N equals ln of e.
Well, we have ln e equals n,
Mhm.
but we're trying to solve for n. Solve for n. So we want to come up with a number that represents what this n is. So we can say e to this number equals this value here. So e to what number equals e?
1.
1. Correct. So e to the 1. So therefore we can say then n is equal to 1. E to the 1 equals e. E to the 1 equals e. That's all we're trying to show there. Does that answer your question?
I think so. Thank you.
You think so? Well, let's take a break and we'll come back. You think about it. We'll take a break. You want a 5-minute or 10-minute break, everybody? What works for you? 5 enough?
That's fine.
Okay. So we'll see you guys in 5 minutes at approximately what, 4:07 or 8, somewhere around there. All right. We'll come back and make sure we understand this problem, and then we'll finish up the lesson. Very good. See you in a bit. Okay, are we back? What questions do you have before we continue? No questions at all? All right. Let's go ahead and take another problem then. Let's see, where do we leave off here? Log base E10. Let's try, well, let's try this one. This looks kind of fun. If I have, make sure we have we done this one before?
Is this still 3.4?
Yes. X plus 1. Have we done this one before? If not, let's go ahead and solve this. If we have done it before, then that's good. You'll know how to do it. If we haven't done it before, we'll take a minute and then we'll go through that. Let's just take a look at this for a minute. See if you know how to solve it. And see if we need to step through this or what we need to do here. And one hint is that we're solving for exponents. So that kind of gives us a hint, doesn't it? That we're going to take, we can take the log of each side. So let's say we take the ln of each side. If I take the ln of 3 to the 2x minus 1 and set that equal to the ln of 7 to the x plus 1, then this becomes a multiplier. So I have 2x minus 1 times, I'll put that one there, I'll just say ln of 3. On the left side, on the right side, this becomes a multiplier, x plus 1, and this is ln of 7. Okay. So then we want to solve for these x's, so we better distribute this ln on the left. So we've got 2x times the ln of 3, and -1 times the ln of 3. So that's just distributing this ln value. And on the right side, let's do the same thing. Let's distribute this ln of 7. So we get x times the ln of 7 plus 1 times the ln of 7. So we should look something like this after distributing on each side. And then let's see if we can gather the terms that have the x's. So this one has an x. This one doesn't, this one does, this one doesn't. So can we get those all on the same side? So let's see, 2x ln 3 minus x ln 7 equals, bring this value to the other side, ln 3 plus ln 7. And it looks like we could factor out the x, couldn't we? We've got an x here and here. So if we factor out that x, we'll have x times 2 ln 3 minus ln 7 equals, and I guess I better put another paren around there, equals ln 3 plus ln 7. And then we'll divide by this value here. So x equals the value on the right, ln 3 plus ln 7 divided by this value here, which is 2 ln 3 minus ln 7. And I guess at this point, we could say that the exact solution is going to look like ln3 plus ln7 over 2ln3 minus ln7. So I'm going to say that's an exact solution. So I'm going to put a box around it, put an arrow to it and say, there's my answer. And by the way, that's the exact answer. And then if I were to put this into my calculator to come up with the decimal, to come up with two decimals, can you guys give me that? What that would look like to two decimals? Have a new volunteer that can tell me what that looks like to two decimals. And then I guess we could also consider using the property of logs to combine the sum of logs into the log of a product. I guess we could do that too, couldn't we? Maybe just do that first while you're working on the sum of what the decimal equivalent would be. We could say the sum of the logs is the log of a product. Well, the log of a product would be the ln of 3 times 7 for the numerator, and 2. And what do I have in the denominator? Do I have anything here? Let's see. If I have 2 here, that becomes an exponent, doesn't it? So that becomes the ln of 3 to the 2 minus the ln of 7. So x equals ln of 7 times 3, that's 21, over, and what do I have here? Can I combine this at all? Let's see, log base e 2ln. I guess that looks like, yeah, that's that squared. Well, I guess that's just 9, isn't it? So that's the ln of 9 minus ln of 7. So in the numerator, ln of 21 over, here we're subtracting. Subtracting gives us a quotient, doesn't it? So that's the ln of 9 over 7. Looks sort of like that. So it looks like if we were to combine these, here we have an exact answer. Looks like we also have an exact answer here. If we were to simplify and combine sum of logs. And this might be easier to convert into an approximate. So x equals, let's see, if I put that, did you guys get something? The ln of 21 is 3.0445, and the ln of 9 over 7 is 0.2513, for instance. So if I do 3.0445 divided by 0.2513, looks like I get 2.11, and that's approximately. What if we did this and said ln of 21 divided by the ln of 9 over 7 and hit enter on our calculator, we get 12.114 again. So either way, it looks like we get an approximate of 12.114 something, rounded off. Okay, so there's several ways we could come up to this answer, two decimals. We could simplify up here and carry all this out and come up with a decimal value. We could combine the sum of logs into products and find out what the decimal is. We could simplify all the way down to here. So I guess this is all the work. This is all the work that we could go through to come up with our answer here. of decimal form 2.11. That makes sense to everybody what we did there and kind of the different approaches we could use to solve that. Questions at all?
So
At the,
if
you can
did
go
the-
ahead.
Sorry, yeah. If you did the first one, the long one, would that be wrong on the test?
This up here?
Yeah.
No, it's not wrong. Just a different form. Depends on what the how the question is phrased. You just want to make sure you answer the question. If you get to this point here, you could leave it that way, or you could say, hey, I could simplify that by saying this is sum of logs, which is the log of a product, and come down to this and come down to this. So these are the same thing. This is just simplified. And this says I'm taking it down to the approximate form to 2 decimals. So either way would work. They're all the same answer. It's just a question of, did you answer the question that was asked?
Professor, does the test clarify whether it needs to be decimal or exact? I guess would be another way to ask Gopal's question. Is it going
Yes.
to tell it? It will.
Yeah, if it says, the question might say, give me the solution set and then give me the approximate to 2 decimals. It might ask for both.
Right. Okay. That makes more sense.
Sure. Other questions?
I'm not sure if I'm just getting confused, but on the beginning when you distributed the 2x minus 1.
Yes, up
Oh,
here.
wait. I think I never mind. I just needed to look at it like again. It
Okay.
was just on the screen, sorry.
Okay. Other questions? We're doing a lot of work here, so I want to make sure that everybody's clear on kind of what we're doing here. Other questions on that at all? Okay. We might be given something that says factor the following. E to the 2x minus 8 e to the x plus 7 equals 0. We might be asked to do that. And you'd say, well, let me think about this. If I rewrite this, I suppose I could rewrite that as e to the x squared minus 8 e to the x plus 7 equals 0. And I could say, well, this might be confusing. I could let a equal e to the x if I wanted to. So this looks like a square minus 8a plus 7 equals 0. And we say, well, let's see here. How am I going to factor this? These are factors. These are ones and ones. So that's going to be a and a. Gives me that. And I have to multiply. So factors here could be, I guess, 1 and 7. That's about it. It's either 1 and 7 or 7 and 1. This says the signs are the same. And this says the signs are both negative. So I can put my negative in here. And then if I FOIL it to make sure it's working, first times first is a squared. Outer is negative a. Inner is negative 7a. And last is negative times negative is a positive 7 equals 0. So let's see, a square minus 8a, combining these two, plus 7 equals 0. So that looks like that works. So this looks like that's the factored form of this. That says that a minus 7 equals 0 and a minus 1 equals 0, or a equals 7 and a equals 1. And we had let a equal e to the x. So that says e to the x equals 7 and e to the x equals 1. Okay, and what are we asked to do here? We done? Well, we're asked to solve for x, aren't we? So if we solve for this x, it's an exponent. So we're going to have to take a log to find out what that exponent is. So I could take the ln of e to the x and the ln of 7 on this one. And the ln of e to the x equals the ln of 1 on that side. And so the ln e to the x. So looking at this left side, ln of e to the x equals what? New volunteer.
X. Never mind.
Thank you. We know you know the answers, Chris. We're going to let other people help us out. Laurel, can you help us out?
For the record, Professor, I'm not trying to show everyone that I know the answer. I just get really impatient
No
when
problem.
people sit in silence.
No problem. Everybody's trying to learn here.
Yeah.
Jacob, what do you think? Or pass to another student. If you'd prefer to pass, just say pass the ball. Jacob, what do you think?
Would it,
Or pass the ball. I'm not putting anybody under pressure. I'm just trying to get everybody to participate.
can you hear me?
Yes, I can hear you.
Oh, all right.
We're looking for the ln of e to the x.
Would it be 1?
Would it be 1? ln e to the x. So this says e to the what equals e to the x. And it's going to be x, isn't it? ln of e to the x is going to be x.
Oh.
Okay. Now I hesitate to give you the answer because you don't learn if I'm just giving you the answer. That's the problem with that approach. That's why I like people to come up with their answers. We can discuss it. Because if Chris gives you the answer or I gave you the answer, we're not learning. We're learning when we participate. Okay. So the ln of e to the x is just x. We have an e down here. We take e to what? E to the x gives us this. Okay, so on the left side, I get x. On the right side, I get ln of 7. So that would be an exact answer. If we left it right like that, we could say that's the exact answer. Or we can put it in our calculator. And I can say, well, let's see. The ln of 7, and that's 1.9. Approximately 1.945, which be 1.95. So I'm going to say here's an approximate answer. Okay. So going down the left side, then I come up with an exact answer of x is the natural log of 7. And if we're asked for it in terms of decimal points to 2 decimals, we could say, well, I can put that in my calculator and get it's approximately 1.95. Make sense to everybody? Questions on what we did there?
Wait, so how'd you change the natural log of e to x again? Could you explain that?
Yeah. Yeah, let me get out another piece of paper here. So if I have ln of e to the x equals some value, we don't know what it is. Well, our base here is e, isn't it? Okay, so if this base is e, and we say e to what is this, well, then n is going to equal x, isn't it? If we say e to this value gives us this, then this value must be x. And that's all we did here. The ln of e to the x is just x. The ln of e to the x equals x. Okay, the log of 10 to the 2 equals what?
Sorry, I'm still trying to like understand at the same time.
No problem, no problem. We need a new volunteer to help us out.
Can I answer?
You may answer.
That would be 2.
And how do we know that?
It's equal log base 10. Yeah, exactly like the one that we just worked on.
Okay, so 10 to the 2 is that. Okay, so 10 to the 2 is 100. So we could also say then that log of 100 equals what? Well, that says 10 to the what equals 100. Well, 10 to the 2 equals 100, doesn't it? 10 to the 2 equals 100.
I have a
Okay.
question, Professor.
Yeah, go right ahead.
So with the previous step of that problem there, when you look at log base 10 of 10 to the 2,
Mhm.
would it be fair to describe it as saying log of any value, or sorry, log of any base to a value that matches that base is equal to the exponent? So we could say log base b of b to the x equals x.
That's true.
Right, so you're just canceling out. If the value and the base are the same, the exponent is your answer. Or is your, yeah. Does that help anyone as like another way of describing it? I only ask because sometimes seeing a problem from more than one angle can help solve it.
That's true. So log base b of b to the x is going to be x. So b to the x equals this.
So did we take the ln of 7 because we did it on the left side?
The ln of 7. That was this problem here. Whatever we do to the left side, we have to do to the right side, don't we?
Okay.
If we multiply left side by 2, we multiply the right side by 2. We have, in order to keep this equation the same, we have to, whatever we do to the left, we do to the right. So we took the ln of the left side to solve for the exponent, which was x. So then we set that equal to the ln of the right side, which is log 7. And if we're asked for an exact answer, we can say, well, then x equals the ln of 7. And if we want an approximate value rounded to 2 decimals, we can just stick this in our calculator, and the calculator will show us 1.5945, whatever, and we can say, well, that rounds to 2 places of 1.95, and this is an approximate value. Other questions? Now, we haven't done the right side over here, have we? So the right side, we have e to the x equals 1. That's what we started with, so that's what we're solving now. We want to solve for e to the x equals 1. And we want to solve for x. So what are we going to do to solve for x? What approach would we use? Trying to solve for that guy right there. Now, also keep in mind, for those of you who are getting frustrated because this is so easy for you, I'm not taking attendance. If you don't want to log on, feel free to log off. There's no requirement for attendance in this class. You're not getting any points for it. You're not losing any points for not being here. But I want to make sure that everybody that does attend gets all their questions asked and answered. So again, we're looking for e to the x. We're trying to solve for x. And what we've discussed is if we're solving for an exponent, because a log is an exponent, we should be able to take the log to find this. And I have a base of e here, so I could take the ln, which is log base e, of e to the x equals ln of 1. Okay, and the ln of e to the x, what do we decide that was? As shown here, what do we decide that was?
X.
X. equals the ln of 1. And what's the ln of 1?
0.
How do we know that?
Anything to the power of 0 equals 1.
Okay, so this is base e. So this says e to the 0 equals what? And it equals 1, doesn't it? So that says e to the 0 power is this thing. So x equals 0 in this case. X equals 0. Okay, it makes sense, everybody? Questions on that at all?
So if the test asked for an exact answer here, so would we just say 0 or would we say ln of 1?
ln of 1 equals, and if that were your solution, you could say, well, here's the ln of 1, and what is the ln of 1 if we want to simplify?
0.
Right. So x equals ln of 1 or x equals 0. So I would bring it down to here.
Okay, thank you.
Mhm. Other questions? Okay. Let's say we have log base 2 of x minus 4. And we set that equal to some value, say 3. And we want to solve. We're solving for x, aren't we? It's the only unknown. Let's solve and check our answer. How about that? Solve for x and check your answer. So what approach could we use to solve log base 2 of x minus 4 equals 3? Have any ideas on how we might set this up to solve for that? New volunteer. Or I can call on a volunteer. Either way works. Selena, what do you think? Or pass the ball. Either way works. Are you with us, Selena?
I would do the log to the both sides.
Okay, so what would you like to do? What should I write down?
Log base 2 times x plus 4 plus log base 2. Equals 3 minus log base 2 x plus 2.
Now this is what we're given. We're given log base 2 of x minus 4 equals 3, and we want to solve for x and then check our value. So this is given.
So the first step I would do is log base 2 times x plus 4 is equal to,
Times x plus 4.
yeah.
Log base 2
X minus 4.
x minus 4, and then you want to do that again.
Yeah, I want to do it. I would do equal to 3.
This is what we have here. You want to set that equal to 3. That's what we have. We're given that.
Yeah, and then 3 minus log base 2 times x plus 4, I think.
X plus 4 like that.
Yeah.
Now keep in mind, log is a function. So when you say log base 2, it's not times x plus 4. It's the log of log using base 2 of this value here. Log is a function. Log on your calculator is a function. Ln on your calculator is a function. So this is not a multiply. Everybody wants to make sure you understand that. This is not multiplied times this. This is a function. Looks like this. Log, if I don't put anything, it's base 10, but this says log base 2. That function operates on something, and it operates in this case on x minus 4. And we're saying that's equal to 3. Okay, we want to make sure that was a good learning point. All right, this is not a multiply. This is a function. So if that's the case, then we're not going to do this. See, I think what the thought was here was, well, we'll use the conjugate, and we'll take the conjugate of x minus 4, and we'll take x plus 4. That's not what we're doing here. There's no conjugate values that we're talking about. But we are talking about knowing that a log is an exponent. This is an exponent of what? Of this base right here. So this base to this exponent gives me this value here. Well, this base to this exponent, 2 times 2 is 4 times 2 is 8. So 2 to the 3 equals 8, and that's equal to this value here. So now we just have to solve this equation for x. So we can add 4 to each side, or x equals 12. Okay. That makes sense to everybody, what we did there?
Could you quickly go over that again?
Yes, I will. Log base 2, x minus 4 equals 3. And I know that a log is an exponent. Here's the exponent, here's the base. So this is 2 to the 3 equals this value here, which is x minus 4. That's essentially the definition of an exponent. X to the n equals y. And if I take the log of each side, log x to the n equals log y. And this becomes a multiplier, n log x equals log y, n equals log y over log x. So just be comfortable with understanding what a log is and how we go from an exponential form to a log form, and even what those look like. Remember, the log form kind of looked like that. Remember that? Okay, so we want to kind of keep in mind not only how we manipulate the function, but what these functions look like. These log functions look like this. They don't have negative values, do they? We can't take some base to some exponent and get a negative value. We can get a small value, but we can't get a negative value. There's no way to take some positive value, whatever this base is, to some exponent and get a negative. So it's always going to be to the right of the y-axis. So in this case here, we're saying here's the base, here's the exponent. So 2 to the 3 equals this. That's really the definition of what the log is. So 2 to the 3 is 8 equals x minus 4. X equals 8 plus 4. That's 12. Okay. Now I can check it. I can say, well, let's see here. What was I given? Log base 2 of x, and x equals 12 minus 4 equals 3. That's what I was given. So log base 2 of 12 minus 4 is 8 equals 3. 2 to the 3 equals 8. So that checks. Okay. So here was the solution. Here's my answer. And here's where I did the check. Now, sometimes the problem might say, give me the solution and then check your answer. Okay, that's what we did here. Okay. Any questions on that before I go to the next section? At this point, I'm going to I don't think I have any new values that I need to. Oh, yes, there is one thing I want to go through before I go to the next section. I want to take a look at an interest rate problem, make sure we're comfortable with that. Remember, we said the amount, if we're doing, this is a compound interest. Compound interest. The amount we receive would be the principal amount we invest plus the interest rate we receive. So if R stands for the interest rate, and N would be the compounding term. Like, is it annually? Is it monthly, quarterly, weekly, semi-annually, whatever it is? So this is the number of compounding terms per year. So if this is 4, that'd be 4 per year times the number of years. So if I said the interest rate is 8% and it's compounded quarterly, that's 4 times per year, isn't it? Times the number of years, and maybe the number of years is 5. So we'd say, well, then this principal, maybe the principal invested is $1,000. So if I invest $1,000 at 8% compounded quarterly for 5 years, how much money do I get back? So, well, let's see, compounded quarterly, so it's n quarters per year for 5 years. If y represents the number of years, then I can put my figures in here. A equals P, which is 1,000 times 1 plus the interest rate. There's the annual interest rate of 8%, which in decimal form is 0.08, compounded quarterly. So I'm going to get 1/4 of that per quarter, but I'm going to compound it 4 times per year times 5 years. So now I just have to put this in my calculator and come up with a value. A equals 1,000 times 1. So this 4 goes into that 2 times, so that's 1.02 to the 20, isn't it? So if I take that value, let's see if I put that in my calculator, what do I get here? 1,000 times 1.02 to the 20, I get 1485 rounded off to 95. Okay, so that tells me that's the amount that I would get at the end of my 5 years. Okay, you might be asked something different. You might say, I'm going to give you this A value. Let's try a different problem. Given A equals 3,600, that's the amount you get back. You invest 1,000 and you do it quarterly, so N equals 4. And you might say, well, how many years do I have to invest that? What is Y? So then the equation would look like 3,600 equals 1,000 times what? 1, and then we're going to add that together, 1.02 to the 4 times the number of years. And now you're going to ask to solve for Y. An exponent. So we might say 1,000, 1.02 to the 4 Y, if Y is the number of years. Solve for Y. Okay, so it's an exponent, probably going to use logs. So 3,600 divided by 1,000, divide each side by 1,000. So I get what? 36 over 10, or 3.6, equals 1.02 to the 4Y. Can I solve for Y? Well, let's see. If I want to solve for this exponent, I might want to take the log of each side. I could take the ln of 3.6 equals the ln of 1.02 to the 4y. This becomes a multiplier. 4y times ln of 1.02. And I'm trying to solve for y. So I'm going to divide through by 4 ln 102. So 4 ln of 1.02. And that's going to be equal to that y value that I'm looking for. So if I rewrite it, y equals the ln of 3.6 over 4 times the ln of 1.02, like that. That I can stick in my calculator, can I? Just put that in my calculator, and I think I get something like 16.2, which says that in approximately, and I guess I should do this, in approximately 16.2 years, 1,000 becomes 3,600 at an interest rate of 8% compounded quarterly. Okay, questions on?
Sorry, could you please move the paper? Thank
Yeah.
you.
Yeah. So I'm going to stop there on 3.4, and we'll spend the rest of the time on 3.5. So let me put all this stuff away, and we'll take out section 3.5. Three 5 talks about exponential growth and decay. So we might have models that both grow and decay. Okay, so let me take a look at, get some clean paper here. Let's say you're given the following. You're giving a table of values, let's say. And this is the year, and this is population. And we're given, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's say the year is 1970 and 1980 and 1990, 2000, 2010, and so forth. And so if we're just taking a look at the number of years since 1970, then I can say, well, 1970 begins at 0, and then we're out here at 10, 20, 30, 40, and so forth. And what we're gonna end up doing is setting up a model to see if we can kind of make some predictions. So we might say, the population here was 202.3 100 million, 203 million, and then it went to 226.5, and then it went to 248.7. I'm just giving you some numbers here, 281.4, whatever these numbers are, 308. It's growing, in other words. So this is the year, and this is population in millions. Okay, so the idea is that apparently we're looking at some sort of a curve that's growing like that, where this is years, and this is some number of people in millions. And so the idea is, if we're asked to come up with a model, an exponential model, something that looks like this, we might say, well, we want some function of time, for instance, that looks like a times b to the kt. We might have some multiplier here. And we'd say, well, if that's the case, if this is what our exponential model looks like, and we're given these values, and we're asked to put these in our calculator to develop some sort of a model here, then the approach would be to develop lists. So I'm going to call this list 1 and this list 2. And the idea of this exercise is to make sure that everyone understands how to put lists into their calculator. Okay, now if you know how to put lists into your calculator and solve for an equation, then this is going to be review. If you don't, then this will be new. And so I could use these values, but I don't need to. These are larger values, maybe harder to deal with, but I could use these values, which are easy. They give me the same description. Number of years since 1970. What does the population look like if this is 1970? And we were at 202.3, and we're looking at what is it out here at these different values. And what are we doing? We're trying to develop an exponential that represents this curve so that we can come out here and predict out here in some year farther out what this population or investment or whatever it is we're modeling is going to be. And I'm just going to take you through an example of how we would set that up. So I'm going to set up list 1 in my calculator, and I'm going to set up list 2 in my calculator, where list 1 is going to be these values here. And I'm going to set it up. I'm going to put it down here on paper, and then I'll do the calculation for you on the calculator. So I'm going to use this left brace, and I'm going to put in the values shown here, 0, 10, 20, 30, 40, and then a right brace, 1, 2, 3, 4, 5 values. These 5 values represents years since 1970. And then I'm going to put in my list 2 the actual population. So here's list 2, and it will contain 202.3 and 226.5 is going to be these values here, and 248.7 and 281.4 and 308.7. Doesn't really make any difference what these are. I'm just using the values given in this table, and then I'll do a right brace here. So I'm just listing what I'm going to do here, and then I'm going to go into my calculator. And before I do that, I might want to take a look at plotting these. And so I take a look at 1970, 80, 90, 2000, 2010, and so forth. And I'll come up with some values here, just like I always would. And I would say, 0 and 202, and that represents this value. And 10 and 226.5, that represents this point. And 20 and 248.7, that represents this point, and so forth. And I plot these points, and I say, well, you know what? That's not a straight line. It looks like it might be some sort of looks like it's going up sort of as an exponential function. And of course, we're in a section dealing with exponential functions. So we're going to say, well, yeah, I think that's what it is because we're in that section. So we say, well, here's list 1, list 2, and I'm going to go to my calculator. I'm going to say, I'm going to hit the stat button, and I'll take you through this in the calculator. And I'm going to go to calculate, and I'm going to say, what do you want to calculate? And I'm going to say, calculate an exponential regression. An exponential regression says, I've got some points out here. They may or may not fall right on this line. They may be up here. They may be down here. Who knows where they're going to be? Maybe these points are sort of out here like this. We don't really know what they are, but it looks like they potentially could be exponential. So I'm going to tell the calculator, you know what? Because I'm thinking this might be exponential. It might not be, but I'm going to make a guess, say it is, and I'm going to have you tell me what the values for A and B should be then if I give you some input. So let's just go ahead and do that. So I'm going to bring out my calculator here, clear it off, make sure my list 1. Okay, so I'm going to put in a list 1. Let me say, so I'll go to my calculator, and here is the brace I'm looking for. It's above the left paren. So I'm going to hit a second on that brace. And I'm going to put in 0, comma, 10, comma, 20, 30, 40. 1, 2, 3, 4, 5 values. That's those are the values I said I was going to use. And I'll finish that with a right brace. So I'll do a second and a right paren, which gives me this brace value here. Let me make sure that all looks good. There's no use going any further if we've got our values wrong. So we got a left brace, 10, comma, 20, comma, 30, and so forth. So that looks good. So I want to put that into list 1. So I've got a store button down here that says, where do you want to store it? I'm going to say I'm going to store it, and where I want to put it here in list 1, which is the second button and above the 1. It says store it in list 1, and then I hit enter. And it says, okay, I've done it. Now, if I want to take a look at list 1, I could do a second list 1 and say, what's in list 1? And it says, that's what's in list 1. 0, 10, 20, 30. So I said, oh, okay, that looks good. That's what I wanted. I've got that done. And then let's set up for list 2. So I'll do my brace, and I'll put the other values that I'm going to put in here, 202.3 and 226.5.
Where do we find the commas, Professor?
Commas are right here. Now you're going to have to be familiar, I guess, with your this isn't a calculator class, but the TI-84 is the calculator we're using, and you're going to use that for other classes that you'll be taking, particularly beyond this one. So you want to be comfortable with where things are, where pi is, where e is, left and right paren, left and right braces, and so forth. So you want to be comfortable with how to use this calculator. And you might want to get a calculator. You might want to get a calculator book. There's one online at ti.com. If you go to ti.com and look in their section, they'll have a manual, a TI-84 calculator manual, if you want to download that. You can also buy books online that show you a TI-84. And you might want to get those so that you know how to enter various values, create lists, and use various functions on the calculator. So let me continue. So 202.3, 226.5. The next value was 248.7. And the next value was 281.4. And the last value was 308.7. And I'll finish that off with a right brace. And I'll store that into L2. And let's take a look then. There's L1. And let's make sure we've got L2. We got the same number here. 1, 2, 3, 4, 5. 1, 2, 3, 4. And we can space over here. 281.4, 308.7. And that ends it. So we've got 1, 2, 3, 4. We had 5 values for each. So we've got the second list set up on our calculator. So that's good. And we know we're going to tell the calculator, we think this is probably going to look sort of like an exponential, because the calculator isn't going to magically pick one. It's going to say, what do you think these things are supposed to look like? So I'm going to say, I'm going to execute the stat button here. So I'm going to hit stat, and then I'm going to say, well, what do I want to do? I want to do a calculate. So I'm going to arrow over to calculate, and I want to find a exponential regression. And I look down here, and I have a linear regression, quadratic, cubic, quartic, linear regression looks like that. LN regression. I want an exponential regression. So let's say I go down to here, and here we go, exponential regression, the 10th one. So I hit that value and say, calculator, I want you to create me an exponential regression. So I'm going to hit enter right there. And the calculator comes back and says, okay, for the exponential regression, what list do you want me to use? You can put any list you want. The defaults are list 1 and list 2, which I have set up. So yes, I'll hit enter to say, yes, use list 1. Yes, use list 2. And these other, I don't really care about. So I'm just going to space past that. And the calculator says, well, for an exponential expression, that looks like the form y equals a times b to the x. Y equals a times b to the x. Your exponential expression for a would be 202.699. And for b, your value would be 1.01067, and however many you want to use. So now I have an exponential equation that I can set up that looks like y equals the original value here, 202.699. That's the value out here for A. The base I'm using is this value here given to me by the calculator, 1.01067. And I'm going to take that to some value, to some exponent. Okay, so if I do that, then I then have developed what my equation would look like. So if I want to set that up and look at that equation, I could enter that. I could go y equals, and if I put in 202, let's say 0.7 times 1.01, forget the rest of that there, and say that's to the x power. And then I'm going to have to set up my window, aren't I? From x minimum to max. And maybe I'm going to do x0 to, I don't know, 5. We'll see how far. Let's see, 1, 2, 3, 4, 5, maybe to 6. Say I go to 6 in increments of 1. And y value goes from, well, let's see, I started out at 202. So I could say, well, start out at 200. Because I started out at 202 here, and I'm going to go up to, well, it looks like somewhere over 3. So I might say, I don't know, 350 or 3 whatever. Let's say 350 in increments. Well, maybe in increments of 50. And then if I graph that, let's see if it comes up with something here that I can look at. Well, it looks like that I'm not getting much of a curve here. I'm not getting much of a curve here. So let's go back and change my window and say, what if I start out at 0 and go to 350 in increments of 50? What is that going to look like? And so it looks fairly flat no matter where I start with, because these values that I gave you were very flat. So that says if I'm using this multiplier, 202.7 times this 1.01, well, that didn't increase it very much. Okay, so we're going to come up with our values, but if that value were larger, say 1.51, and I were to graph that, you can see how much more quickly it's growing. So the values you put in here are important based on what your graph is going to look like. So we now have developed the equation that can be used to predict what the values for population would be farther out, say 2010, 2020, 2030, and so forth. So all we're doing then is using the input list 1 and list 2 to determine what the model should look like. Okay, I just want to take you through that before we exit it today. Okay, questions on how we would build that model at all? All right, that's all I have for today. The next time I see you is going to be when?
Wednesday.
Wednesday. And what are we going to do on Wednesday?
Test.
Test on Wednesday on chapter
3.
3. Very good. All right, everybody. Good work. We'll see you Wednesday. It'll be the same procedure. You should have 10 questions and an hour or two to finish those 10 questions. Okay.
Thank you.
Thank you, Professor.
All right, everybody. We'll
Thank
see
you,
you
Professor.
on Wednesday.